Today we'll discuss 15 very important inequalities which are imperative to mathematics Olympiad preparation. You'll find that many of these inequalities are also helpful for your JEE, ISI and CMI preparation. So we'll start with the first inequality, and that's your fundamental AM, GM and HM inequality. So the very first inequality is AM, GM, HM inequality. If we have n positive real numbers a1, a2, a3 up to an, where each of these numbers they are positive real numbers, then we can define their arithmetic mean as their sum a1 plus a2 up to an whole divided by n, their geometric mean as their product a1, a2 an to the power 1 by n, and their harmonic mean as n upon 1 upon a1 plus 1 upon a2 up to 1 upon an. Now relationship between the three means is arithmetic mean is always greater than or equal to geometric mean, that is always greater than or equal to harmonic mean for positive real numbers. So for positive real numbers, their arithmetic mean will always be greater than their geometric mean and will always be greater than their harmonic mean. Now here we have two cases. Case 1, we have this equality sign AM, it is equal to GM and it will be equal to HM if and only if all the numbers are same. So this equality sign is only possible when all these numbers they are same. And we have this second condition when at least one AI is unequal to AJ or numbers are distinct. So at least we have one number which is different from all other numbers. In that case, arithmetic mean is always strictly greater than their geometric mean and will be strictly greater than their harmonic mean. Now since this AM it is related to sum and GM it is related to product, you'll find many situations where it will be given that either sum is constant or product is constant. So if sum is constant, they'll ask you to find maximum value of the product, and if product is constant, then they'll ask you minimum value of the sum. So these are some common problems that you'll find in AM, GM and HM inequality. Now this inequality is so fundamental that it is extensively used in every portion of mathematics. Now let us take up some examples. Now the first question is, if A, B, C are three positive real numbers, so we have three positive real numbers, so A, B, C, they are positive real, then which of the following is or are true? Now this first one is A square plus B square plus C square, it is greater than or equal to BC plus CA plus AB. So for this first one, what we'll do is, we'll take three numbers as A square, B square and C square, and we'll write their arithmetic geometric mean inequality taking two at a time. So if we take A square and B square, we can write A square plus B square by 2. It is greater than or equal to A square B square to the power 1 by 2, which is simply AB. In the same way, we can write it for B square and C square. So B square plus C square by 2, it is greater than or equal to BC, and C square plus A square by 2, it is greater than or equal to CA. Now, if we add all these three, then in the numerator we'll have 2 times A square plus B square plus C square whole divided by 2 and will be greater than or equal to AB plus BC plus CA. Now we can cancel this 2 with 2. So we'll get this result as A square plus B square plus C square, it is greater than or equal to AB plus BC plus CA. That means this option A is correct. Now this result, it is an important result in mathematics, and the version which is mostly used in JEE Advanced is this version. You'll be given A square plus B square plus C square and it is equal to AB plus BC plus CA. Now we know that we'll have this equality when AM is equal to GM. And AM is equal to GM if and only if numbers are same. So from here we'll get this condition that A must be equal to B, it must be equal to C. So if we have this strict equality, then all three numbers, they'll be same. Another way to solve the same question is, we can write this as A square plus B square plus C square minus AB minus BC and minus CA. Now what we'll do is, we'll multiply and divide everything with 2. So we can write this as 1 by 2 and it'll be this 2A square plus 2B square plus 2C square minus 2AB minus 2BC minus 2CA. Now we'll take A square plus B square and 2AB. Then we'll take B square plus C square 2BC. And then we'll have A square plus C square minus 2CA. So we can write this as 1 by 2. And here will be this A minus B square plus B minus C square plus C minus A whole square. Now we know that sum of squares is always greater than or equal to 0. So from here again we can write A square plus B square plus C square will be greater than or equal to AB plus BC plus CA, and we'll have this equality sign if each of the squares is 0. That means we'll have this equality sign, that is A square plus B square plus C square, it is equal to AB plus BC plus CA if A is equal to B and B is equal to C. So that's our option A. Now we'll come to this option B. Now option B is direct application of AMGM. So we have three numbers, A cube, B cube and C cube. They are all positive real numbers. We can write their arithmetic mean. So it will be A cube plus B cube plus C cube by 3. It will be greater than or equal to their geometric mean. So there will be A cube, B cube, C cube to the power 1 by 3, which is ABC. So if we rearrange, we can write A cube plus B cube plus C cube. It is always greater than or equal to 3 times ABC, which means this option B is also correct. Another way to write this is, we know that A cube plus B cube plus C cube minus 3ABC, it is A plus B plus C into A square plus B square plus C square minus AB minus BC and minus CA. Now we know that ABC are all positive real numbers, so this is a positive real number, and in the first part we have proved that this expression is always greater than or equal to 0. So from here again we can write A cube plus B cube plus C cube, it is greater than or equal to 3ABC. Now we'll come to part C. In part C, we are given three products and we have to prove that it is greater than or equal to 8ABC. Now here what we'll do is, we'll take three numbers as ABC and we'll write their AMGM, again taking 2 at a time. So we can write A plus B by 2. It is greater than or equal to under root AB. B plus C by 2. It is greater than or equal to under root BC, and C plus A by 2, it is greater than or equal to under root CA. Now we multiply all these three, we can write A plus B into B plus C into C plus A whole divided by 8, and it is greater than or equal to under root A into under root A. So there will be A, in the same way it will be B and C. So we can write it is greater than or equal to ABC, or simply A plus B into B plus C into C plus A. It is greater than or equal to 8 ABC. That means this option C is also correct. Now this option D is, we need to prove that BC upon A plus CA upon B plus AB upon C, it is greater than or equal to A plus B plus C. Now for this, what we'll do is, we'll divide everything with ABC. So we can write 1 upon a square plus 1 upon b square plus 1 upon c square will be greater than equal to 1 upon bc plus 1 upon ca plus 1 upon ab. So this first inequality, it is equivalent to its second form. Now we'll prove this the way we have proved this first one. So it is same as this first one, but in case of ABC, we are taking 1 upon a, 1 upon b and 1 upon c. So we can write 1 upon a square plus 1 upon b square by 2 will be greater than equal to their geometric mean, which is 1 upon ab. In the same way, 1 upon b square plus 1 upon c square by 2, it is greater than equal to 1 upon bc and 1 upon c square plus 1 upon a square by 2. It is greater than equal to 1 upon ca. Now if we add all these three, we'll get this result. That means this statement D is also correct. So the correct options are A, B, C, D. Let us take another example. Now here the question is, find the maximum value of this expression for x greater than 0. So here x is a positive number. Now our expression is y equals x plus 1 upon x to the power 6 minus x to the power 6 plus 1 upon x to the power 6 minus 2 upon x plus 1 upon x whole cube plus x cube plus 1 upon x cube. Here what we'll do is we'll take this minus 2 with this second expression. So we can write this as minus, and here will be this x to the power 6 plus 1 upon x to the power 6 plus 2, which actually is a square plus b square plus 2ab. So we can write this as y equals x plus 1 upon x whole to the power 6 minus, and here it is x cube plus 1 upon x cube whole square whole divided by x plus 1 upon x whole cube plus x cube plus 1 upon x cube. Now what we'll do is, in the numerator we have x plus 1 upon x to the power 6. We'll write this as x plus 1 upon x to the power 3 whole to the power 2. Now this is a square minus b square. So using the formula, we can write this as y equals a plus b, and there will be x plus 1 upon x whole cube plus x cube plus 1 upon x cube into a minus b, and that will be x plus 1 upon x whole cube minus x cube minus 1 upon x cube whole divided by x plus 1 upon x whole cube plus x cube plus 1 upon x cube. Now this expression, it gets cancelled. So now we can write this as y equals x plus 1 upon x whole cube minus x cube minus 1 upon x cube. Now this is a plus b whole cube, so there will be a cube plus b cube plus 3a square b plus 3ab square, and then we have this minus x cube minus 1 upon x cube. Now these two, they get cancelled. So this y will be 3 times x plus 1 upon x. Now we have to find minimum value of their sum, and we know that if we multiply them, their product is 1. So their GM will be constant. So here we'll use AM and GM. So if we use AM and GM, we can write x plus 1 upon x by 2. It is greater than or equal to under root of x into 1 by x, which is 1. So we can write this as this x plus 1 by x. It is greater than or equal to 2. If x plus 1 upon x is greater than or equal to 2, then this y, it is greater than or equal to 6. So minimum value of this expression will be simply 6, and that is the answer to this question. Now the second inequality is weighted AMGM inequality. So suppose we have n positive real numbers a1, a2, a3 up to an, where each of ai, it is a positive real number, and we have n positive rational numbers, which are suppose w1, w2, w3 up to wn, and we'll take them as weights of a1, a2, a3 and an. So these wi's, they are positive rational numbers. Then we can write their weighted arithmetic mean as this am star, and it will be w1a1 plus w2a2 up to wn upon w1 plus w2 up to wn, and we can write their weighted geometric mean as a1 to the power w1, a2 to the power w2 and an to the power wn whole to the power 1 upon w1 plus w2 up to wn. Now let us take an example. Say for example we have three positive real numbers a, b and c. So these a, b and c, they are positive real numbers, and let us consider their weights as 1, 2 and 3. Then we can write their weighted am as 1 into a plus 2 into b plus 3 into c upon 1 plus 2 plus 3, and there will be a plus 2b plus 3c upon 6, and we can write their weighted gm as a to the power 1, b to the power 2, c to the power 3 whole to the power 1 upon 1 plus 2 plus 3, and there will be a b square c cube to the power 1 by 6. So this is how we write weighted AMs and weighted GMs. Now if we closely look at these weighted AMs and GMs, it simply means that we are considering numbers in which A is taken one time, we have taken this B 2 times, and we have taken this C 3 times. So it will be this A, B, B, C, C, C. If we write their arithmetic mean, it will be A plus B plus B plus C plus C plus C whole divided by total numbers is 6. So there will be A plus 2B plus 3C whole divided by 6. So essentially it is arithmetic mean of 6 numbers rather than 3 numbers. In the same way, if we write their geometric mean, it will be A into B into C into C into C whole to the power 1 by 6, which is A B square C cube to the power 1 by 6. So basically they are AM and GM of these 6 numbers. Now here the fundamental is, if AM star is weighted AM of these n numbers and GM star is weighted GM of these n numbers, then their weighted arithmetic mean will always be greater than or equal to their weighted geometric mean. So weighted AM is always greater than or equal to weighted GM for n positive real numbers having positive rational weights. And again here we'll have this equality. So this AM star will be equal to GM star if and only if A1 equals A2 equals AN. Now let us take up an example. We are given that x, y and z are positive real numbers. So x, y and z, they are positive real numbers such that x into y into z, it is equal to 32. Then we have to find minimum value of x square plus 4xy plus 4y square plus 2z square. Now clearly we know we have to find minimum value of sum, and we are given something of this product x, y, z. So we have to use AM and GM. But the problem here is, if we want to multiply these 4 expressions, then we get x square into 4xy into 4y square into 2z square, and then we'll have x cube, y cube and z square. So we'll get this expression as xy cube into z square, but we are given that x into y into z is constant. So this expression on the geometric mean side, it won't be a constant, so you won't be able to get this minimum value. Now this problem can be resolved if we want to use weighted AMGM. So what we'll do is, we'll consider four numbers as x square, 2xy, 4y square and z square, and we'll consider their weights as 1, 2, 1 and 2. Now if you want to write their weighted arithmetic mean, it will be x square plus 2 into 2xy plus 4y square plus 2z square upon 1 plus 2 plus 1 plus 2. So their weighted AM will be x square plus 4xy plus 4y square plus 2z square whole divided by 6. Now we can write their weighted GM. It will be x square and then 2xy whole square, 4y square to the power 1 and then z square whole to the power 1 by 6. Now it will be 2 square into 4, there will be 2 to the power 4, then x square into x square, x to the power 4, y to the power 4 and z to the power 4 whole to the power 1 by 6. Now we can write this as 2xyz whole to the power 4 by 6. Now x into y into z is 32. So this is 64 and 64 is 2 to the power 6. So we can write this as 2 to the power 6 whole to the power 1 by 6. I'll cancel. This is 16. We know that weighted AM is always greater than or equal to weighted GM. So from here we can write x square plus 4xy plus 4y square plus 2z square divided by 6 is always greater than or equal to 16. So from here we can write x square plus 4xy plus 4y square plus 2z square is greater than or equal to 16 into 6, and it is 96. So minimum value of this expression is 96. That means the correct option is this option C. Now let us take another example, and it says the minimum value of sum of real numbers a to the power minus 5 plus a to the power minus 4 plus 3 a to the power minus 3 plus 1 plus a to the power 8 plus a to the power 10, where a is greater than 0. Now we have to find minimum value of this sum, and each of these numbers, they are positive real numbers. So clearly we can use AM and GM. But the problem here is, if we multiply the powers of a, it will be a to the power minus 5 into a to the power minus 4 into a to the power minus 3 into a to the power 8 and a to the power 10. Now these negative powers, they come to a to the power minus 12, and these positive powers are a to the power 18. So their GM, it won't be constant, but we have this 3 here. So if we consider this a cube 3 times, then we'll have a to the power minus 18 here, and in that case this GM will be a constant number. So for this question, we'll consider these 6 numbers: a to the power minus 5, a to the power minus 4, a to the power minus 3, 1, a to the power 8 and a to the power 10 with weights 1, 1, 3, 1, 1 and 1. And if we write their weighted AM, it will be a to the power minus 5 plus a to the power minus 4 plus 3 a to the power minus 3 plus 1 plus a to the power 8 plus a to the power 10 whole divided by, now this is 3 plus 3, 6 plus 2, 8. and their weighted GM, it will be a to the power minus 5 into a to the power minus 4 into a to the power minus 3 cube into 1 into a to the power 8 into a to the power 10 whole to the power 1 by 8. Now this is a to the power 0, which is 1. So the GM will be 1. Now again we are to use weighted AM and weighted GM. So weighted AM star will be greater than or equal to weighted GM. So we can write a to the power minus 5 plus a to the power minus 4 plus 3 a to the power minus 3 plus 1 plus a to the power 8 plus a to the power 10 divided by 8. It is greater than or equal to 1, or simply we can write a to the power minus 5 plus a to the power minus 4 plus 3 a to the power minus 3 plus 1 plus a to the power 8 plus a to the power 10 is always greater than or equal to 8. Therefore, its minimum value is simply 8. That means answer to this question is this option C. Now the third inequality that we'll study is mth power arithmetic mean. So if we have n positive real numbers, say a1, a2, a3 up to an, and they are all positive real numbers, and we have a real number m, then we have three cases depending on the value of m. The first case is if m belongs to r minus 0, 1, that is either m is less than 0 or m is greater than 1. In that case, arithmetic mean of mth power of these numbers, which is a1 to the power m plus a2 to the power m up to an to the power m whole divided by n, will be greater than or equal to mth power of their arithmetic mean. So it will be greater than or equal to a1 plus a2 up to an by n whole to the power m. So this is true if m is less than 0 or m is greater than 1. Now we take an example. Say for example, we consider m as 2. Then this left hand side will be a1 square plus a2 square up to an square by n, which is arithmetic mean of their squares, and will be greater than or equal to square of their arithmetic mean, and which is a1 plus a2 up to an upon n whole square. Now this m, it can be a negative number also. We can take this m as, say, minus 1 by 2. Then we can write a1 to the power minus 1 by 2 plus a2 to the power minus 1 by 2 up to an to the power minus 1 by 2 by n, and will be greater than or equal to a1 plus a2 up to an by n whole to the power minus 1 by 2. So this is our first case when m is either less than 0 or greater than 1. Now we have the second case when m lies between 0 and 1. So the second case when m lies between 0 and 1, in that case, sign of inequality, it reverses. So simply we can write a1 to the power m plus a2 to the power m up to an to the power m whole divided by n will be less than or equal to a1 plus a2 plus an upon n whole to the power m. So if m lies between 0 and 1, then the sign of this inequality, it changes. So if we take an example, suppose we consider m as 1 by 3, we can write a1 to the power 1 by 3 plus a2 to the power 1 by 3 up to an to the power 1 by 3 whole divided by n will be less than or equal to a1 plus a2 up to an by n whole to the power 1 by 3. And then we have this third and trivial case if m belongs to this set containing 0 and 1. So if m is 0 or m is 1, in that case both the expressions, they'll be equal. So we can write a1 to the power m plus a2 to the power m up to an to the power m whole divided by n will be equal to a1 plus a2 up to an by n whole to the power n. So we have this equality when the value of m is either 0 or 1. Now let us take one example. It says prove that under root 1 plus under root 2 up to under root n, it is less than n into under root n plus 1 by 2. So here what we'll do is we'll consider n numbers 1, 2, 3 up to n, and we'll consider their mth power am's using m as 1 by 2. Now since m lies between 0 and 1, we have to use its second form. So we can write 1 to the power 1 by 2 plus 2 to the power 1 by 2 up to n to the power 1 by 2 whole divided by n will be less than. And here we are using this strict inequality because all these numbers, they are distinct, they cannot be equal. So it will be less than square root of their arithmetic mean, which is 1 plus 2 plus 3 up to n whole divided by n to the power 1 by 2. Now we can write this as under root 1 plus under root 2 plus under root 3 up to under root n divided by n, and it will be less than, this is sum of first n natural numbers. So it will be n plus 1 upon 2, and here we have this n to the power 1 by 2. Now this n will cancel, so it will be under root of n plus 1 by 2. Now if we rearrange, we can write this as under root 1 plus under root 2 plus under root 3 plus under root n will be less than n into under root of n plus 1 by 2, which is what we need to prove in this question. Now let us take another example, and this is too small, so what I'll do is I'll write the question. Now it says let a, b, c be 3 positive real numbers. So we have 3 positive real numbers a, b, c. They are all greater than 0 such that a plus b plus c is 1. Then we have to find minimum value of 1 upon a square plus 1 upon b square plus 1 upon c square. Now here what we'll do is we'll use mth power am for ABC considering m as minus 2. Now we know that a to the power minus 2 plus b to the power minus 2 plus c to the power minus 2 upon 3 will be greater than or equal to a plus b plus c by 3 whole to the power minus 2. Now it is given that a plus b plus c is 1. So it will be 1 upon 3 to the power minus 2, which is 9. So from here we can write 1 upon a square plus 1 upon b square plus 1 upon c square will be greater than or equal to 27. So minimum value of this expression is 27, and that is the answer to this question. Now the fourth inequality that we'll study is power mean inequality. Now before learning this inequality, we must understand power means. If we have n positive real numbers a1, a2, a3 up to an, and they are positive real numbers, and we have a real number k which is unequal to 0, then their power mean mk a1, a2, a3 up to an, it is defined as a1 to the power k plus a2 to the power k up to an to the power k whole divided by n to the power 1 upon k, where k is a real number and it is not equal to 0. To understand this, let us consider power mean of AB if k is 3. Now it will be this a cube plus b cube by 2 whole to the power 1 by 3. So this is how we write power mean of these numbers with the given k. Now the fundamental here is, if we have non-zero real numbers k1 and k2 such that k1 is greater than k2, then mk1, a1, a2, an is always greater than equal to mk2, a1, a2 up to an. So that is the fundamental for power means. So if we have three positive real numbers a, b and c, then we know that 3 is greater than 2 and it is greater than 1. Then we can simply write m3abc will be greater than equal to m2abc and will be greater than equal to m1abc, which simply means a cube plus b cube plus c cube upon 3 to the power 1 by 3, it will be greater than equal to a square plus b square plus c square upon 3 to the power 1 by 2 and will be greater than equal to a plus b plus c by 3. So this is how we are going to use power mean inequality. Now let us take up an example. Say for example, it says if a, b, c are positive real numbers, so we have positive real numbers a, b and c, and we have to prove that 9 a cube plus b cube plus c cube is greater than equal to a plus b plus c whole cube. We can solve this question using mth power am. Here we are going to solve it using power mean inequality. Now we know that m3abc will be greater than equal to m1abc. Now m3abc is a cube plus b cube plus c cube upon 3 to the power 1 by 3 and will be greater than equal to a plus b plus c by 3. Now if we take cube both sides, then we can write a cube plus b cube plus c cube upon 3 will be greater than or equal to a plus b plus c whole cube upon 27. Now we can cancel this 3 with 27, so it will be this 9. So if we rearrange, we can write 9 times a cube plus b cube plus c cube will be greater than equal to a plus b plus c whole cube, which is what we need to prove in this question. Now let us take another example, and here we have to prove that a cube plus b cube plus c cube upon a square plus b square plus c square is greater than equal to a plus b plus c by 3. Now again for this, we'll take three positive real numbers a, b, c, and again we know m3abc is greater than equal to m2abc. So we can write a cube plus b cube plus c cube upon 3 to the power 1 by 3 is greater than equal to a square plus b square plus c square upon 3 to the power 1 by 2. Now if we take square both sides, then we can write a cube plus b cube plus c cube upon 3 to the power 2 by 3 will be greater than equal to a square plus b square plus c square upon 3. So that's our first inequality relationship. Now we also know that m3 is greater than equal to m1. So we can write m3abc will be greater than equal to m1abc. So it will be this a cube plus b cube plus c cube upon 3 to the power 1 by 3 and will be greater than equal to a plus b plus c whole divided by 3, and that's our second inequality relationship. Now what we'll do is we'll multiply these two. Now this is a cube plus b cube plus c cube upon 3 to the power 2 by 3 plus 1 by 3. So this part will be 1. So we multiply it, we get a cube plus b cube plus c cube upon 3 and will be greater than or equal to a square plus b square plus c square into a plus b plus c whole divided by 9. Now this 3 and 9 will cancel. And if we rearrange, then we can write a cube plus b cube plus c cube upon a square plus b square plus c square will be greater than or equal to a plus b plus c by 3, which is what we need to prove in this question. Now the fifth inequality that we want to study is triangle inequality. Though this inequality is a very simple inequality, but it has very wide applications in multiple fields and gives an access to very interesting inequalities. Now here the inequality is, if there is a triangle ABC whose side lengths are small a, small b and small c, then we know that triangle inequality dictates sum of two sides of a triangle is always greater than the third side. That means we can write a plus b will always be greater than c, b plus c will always be greater than a, and c plus a is always greater than b. So if ABC are sides of a triangle, then ABC must follow this relationship. Now let us take one example. It says if ABC are sides of a triangle, so we have if ABC are sides of a triangle, then the value of expression a upon b plus c plus b upon c plus a plus c upon a plus b cannot exceed. Now, if you closely look at this inequality, it has a setting of a famous inequality called as Nesbit's inequality. And Nesbit's inequality is if a, b and c, they are positive real numbers, then a upon b plus c plus b upon c plus a plus c upon a plus b, it is always greater than or equal to 3 by 2. We have already proved this inequality using 12 methods. So for any positive real numbers, this sum will always be greater than or equal to 3 by 2. Now clearly this inequality, it has a lower bound. We are talking about its upper bound considering ABC as sides of a triangle. Now for this, what we'll do is we'll let a plus b plus c as 2s, where s is semi-perimeter. Now we know that b plus c will be greater than a. Now if we add b plus c both sides, we can write 2 times b plus c will be greater than a plus b plus c, which is 2s, or simply we can say b plus c is greater than s. So we can write b plus c is greater than s. In the same way, c plus a is greater than s and a plus b is greater than s. Now if we take the reciprocal, we can write 1 upon b plus c will be less than 1 upon s. 1 upon c plus a will be less than 1 upon s, and 1 upon a plus b will be less than 1 upon s. Now if we multiply this first one with a, so you get a upon b plus c, it is less than a upon s. In the same way, b upon c plus a will be less than b upon s, and c upon a plus b will be less than c upon s. Now if we add all these three, we can write a upon b plus c plus b upon c plus a plus c upon a plus b will be less than a plus b plus c upon s. Now a plus b plus c is 2s, so it is always less than 2. So from here we can write this value, it cannot exceed 2, and that's your option C.
Today we'll discuss an interesting problem in geometrical probability, and the question goes like, if you break a pencil in 3 parts, what is the probability that the 3 parts can be arranged to form a triangle? Suppose we have this pencil, and suppose length of this pencil is L. Now we have to break this pencil in 3 parts. Suppose these are the 3 parts. Now suppose length of this first part is X, length of this second part is Y, and length of this third part will be L minus X minus Y. Now first we'll find uniform sample space for this given condition. So we know that this X, it should be greater than 0 but less than L. In the same way, Y also should be greater than 0 but less than L. And the third one, which is 0, is less than L minus X minus Y, and it should be less than L. Now here we know that X and Y, they are both positive. So from the third one, we'll get this condition as X plus Y is less than L. So we have 3 conditions. So X should lie between 0 and L, Y should lie between 0 and L, and X plus Y should be less than L. So we'll plot this region on a coordinate plane. So X, it takes the value from 0 to L. In the same way, Y takes the value. So this is X and this is Y. So Y takes the value from 0 to L. So we have this region, which is this square. And then this third condition, which is X plus Y is less than L. So I'll draw this line, which is X plus Y is equal to L. So it'll be the straight line passing through these 2 points. And then X plus Y is less than L. So if I'll put origin, so 0 is less than L, which is true. So that means we can break this pencil in 3 parts whose sample space can be represented by this uniform area, and which is area of this triangle. Now we need to find this condition that these 3 parts, they can be arranged to form a triangle. Now let 3 sides of a triangle be A, B and C. Now we know that A, B, C are sides of a triangle if they satisfy triangle inequality, and triangle inequality is sum of 2 sides is greater than the third side. So that means A plus B should be greater than C, B plus C should be greater than A, and C plus A should be greater than B. Now I will take A plus B. So what is A plus B? A plus B is X plus Y should be greater than L minus X minus Y. So from here I'll get X plus Y should be greater than L by 2. Now from the second one, B plus C is greater than A. So what is B? B is Y, and this is plus L minus X minus Y. It should be greater than X. So here Y will cancel. So here I'll get X should be less than L by 2. And from the third one, C plus A, C is L minus X minus Y plus X, and it should be greater than Y. So here I'll get Y should be less than L by 2. So the condition that these 3 parts, they can be arranged to form a triangle is this X plus Y should be greater than L by 2, X should be less than L by 2, and Y should be less than L by 2. So I'll mark this region. So I'll take X as L by 2, So this is x is L by 2, and then I'll also have this y equals L by 2. So here x should be less than L by 2 and y should also be less than L by 2. So we have this square. And now this third condition is x plus y should be greater than L by 2. So first I'll draw this line, which is x plus y equals L by 2. Now this point is L by 2 comma 0. This is 0 comma L by 2. So I'll draw this line. So this is x plus y equals L by 2. Now if I'll put x and y as 0, I'll get 0 is greater than L by 2. So that means 0 doesn't satisfy this equation. So the area or the region that we'll need is above this line. So the condition that these three parts can be arranged to form a triangle corresponds to this blue triangle. Now we'll calculate this probability that these three pieces, they'll form a triangle. So what is the favorable area? Favorable area is this area of blue triangle. So this is half. Now what is the length of this side? So it is L by 2, and this also is L by 2. So half L by 2 into L by 2. And then what is the total area in the problem? Area of this black triangle, so which is 1 by 2, and then length of this side is L. This side is also L, so that is L into L. So half will cancel, L will also cancel. So this is 1 by 4. So which simply means if you have a pencil and if you randomly break it in three parts, then it is 25% chance that these three pieces will form a triangle. Now question number 8, it is very interesting question. It says how many non-congruent triangles are there with integral lengths a less than equal to b is less than equal to c such that a plus b plus c is equal to 20. Now since a, b, c, they are sides of a triangle, they cannot be negative. So what we'll do is we let a as say 1 plus x1 where x1 is greater than or equal to 0. So we have substituted a with 1 plus x1. That is the minimum value of a can be 1. Now b is greater than a. So we can write this b as b equals a plus x2. So that means this b will be at least as large as a. So we can write this as 1 plus x1 plus x2, where again x2 is greater than or equal to 0. And in the same way, this c is greater than b. So we can write c as say b plus x3. So which simply means we can write this as 1 plus x1 plus x2 plus x3, where x3 is also greater than 0. Now we are given this condition that a plus b plus c is 20. So we'll add them, then we'll get 3 plus 3x1 plus 2x2 plus x3, and this should be equal to 20. So we can write this equation as 3x1 plus 2x2 plus x3, and it should be 17, where each of x1, x2 and x3, they are integers greater than or equal to 0. So this is the condition that we have when a plus b plus c is 20 and a is less than or equal to b is less than or equal to c. Now we'll need one more condition, that these three lengths, they'll form a triangle. So three numbers, they'll form a triangle if they satisfy triangle inequality, and which is sum of two sides must be greater than this third side. So that means from here we'll also need to write a plus b must be greater than c. Now what's a plus b? A plus b is 2 plus 2x1 plus x2, and it should be greater than 1 plus x1 plus x2 plus x3. Now here x2 will cancel, x1 will also cancel once. So simply we can write 1 plus x1, it should be greater than x3. So we'll need to find solution to this equation provided x3 is less than 1 plus x1. So now we'll put in the values of x1, x2 and x3, and then we'll see how many such triangles are possible. So we'll consider the values of x1, x2 and x3. Now we'll take x1 as 0. Then in that case, we'll get this equation as 2x2 plus x3 is equal to 17. Now we also know that x3 is less than 1 plus x1. So that means x3 is less than 1. So the only value possible for x3 is 0. Now x3 has to be an odd number to get an integral solution. So that means for x1 equals to 0, we won't get any solution. Now when x1 is equal to 1, we can write 2x2 plus x3, and this is 17 minus 3. 17 minus 3 is simply 14, where x3 is less than 2. Now in this case, 2x2 plus x3 is 14. So that means x3 can take only even values. So the only even value possible in this case is x3 equals 0. So that means we have one triangle in which x1 is 1, x3 is 0, and if we'll put x3 as 0, we'll get x2 as 7. Now we'll take x1 as 2. So we'll take x1 as 2, we'll write 2x2 plus x3, and it'll be 11. And here x3, it is less than 3. Now again x3, it has to be an odd number. So the only odd number possible in this case is x3 equals to 1. So that's our second triangle possible. Now we'll take x1 as 3. Then it will be 2x2 plus x3 equals to 8, where x3 is less than 4. Now here x3 has to be an even number. So we have two values of x3 possible. Either x3 is 0 or x3 is 2. So it will give us two more triangles. Now we'll take x1 as 4. Then we can write 2x2 plus x3 is equal to 5. Now where x3, it should be less than 5. Now x3 take odd values. So value of x3 can be either 1 or value of x3 can be 3. So we have two more triangles. And then finally we'll have x1 equals 5. So we'll get 2x2 plus x3, and this is equal to 2, where x3 is less than 6. Now in this case, x3, it has to be an even number. Since this value is 2, so x3 can take only two values, and which is either the value of x3 is 0 or the value of x3 is 2. So we'll need to count number of triangles possible. So we have one triangle here, and then we have one triangle here. We have two triangles here, two more, and then finally we'll have two more triangles. So it'll be 6 and 2, 8. So number of such triangles possible is simply 8, and that is the answer to this question.
Now the sixth one, it's a very common inequality and it is extensively used in calculus, and the inequality is sin x, it is less than equal to x, and it is less than equal to 10x when x lies between 0 to not included pi by 2. Now how do we prove this? One of the way of proving this inequality is using calculus. So we'll consider function fx, which is sin x minus x when x lies between 0 to pi by 2. Now if we find f dash x, it will be cos x minus 1, which is less than equal to 0. That means fx is strictly decreasing, and if x is greater than equal to 0, that means fx is less than equal to f0. Now what's f0? f0 is 0. So from here we can say sin x minus x, it is less than equal to 0, or simply sin x is less than or equal to x. Now for this next part, again we'll consider function gx when x lies between 0 to pi by 2, and let that function be x minus 10x. G dash x will be 1 minus secant square x, which is minus 10 square x, again less than equal to 0. So this gx, it is also a decreasing function. So again, when x is greater than equal to 0, gx is less than equal to g0. Now g0 is 0 minus 0. So gx is less than equal to 0, or x minus 10x is less than equal to 0. So from here we can say x is less than equal to 10x, which completes our proof that when x lies between 0 to pi by 2, sin x is less than x, and it is less than 10x, and we have this equality sign when x is equal to 0. Now, one of the use of this inequality is when we're going to plot this graph of sin x, x and 10x in 0 to pi by 2, then this is, suppose y is equal to x line. Now sin x will be less than x, so it will be drawn below this graph, and since 10x is greater than x, graph of 10x will lie above this y is equal to x line. Now let us take an example. The smallest positive root of this equation, 10x minus x equals 0, lies in. So we have this equation which is 10x equals x.
I'll draw the graph of 10x and I'll draw the graph of y equals x line. So first I'll draw the graph of 10x. So that's the graph of 10x. Now I'll draw the graph of y equals x line. Now what I clearly know is calculus inequality says sin x is less than x is less than 10x when x belongs to 0 to pi by 2. That means the graph of y equals to x line will lie below the graph of 10x in the first quadrant. So that is the graph of y equals x line. Now these two graphs, they intersect in the third quadrant. So answer to this question will be C. So the smallest positive root of this equation will lie in pi to 3 pi by 2. So whenever we are solving problems related to sin, 10 and x, we must remember this inequality. So if I draw the graph of sin x also, now sin x will lie below x. And that's how we'll draw the graph of sin, 10 and y equals to x line.
Let us take another example. Here we are given a complex number z and we have to prove mod of z upon mod z minus 1 is less than or equal to mod of argument of z. Now here we let z as r cos theta plus iota sin theta. Now here mod of z is r and argument of z is theta. Now if we take this left hand side, it is mod of z upon mod z minus 1 and will be this r cos theta plus iota sin theta upon r minus 1. Now this r and r will cancel, so we can write this as mod of cos theta minus 1 plus iota sin theta and will be this under root of cos theta minus 1 whole square plus sin square theta. Now we can write this as under root of, now cos square theta plus sin square theta is 1 plus 1 square minus 2 cos theta. So it will be this under root of 2 1 minus cos theta. Now we'll use half angle formula. So it will be this under root of 2 and then 1 minus 2 sin square theta by 2. Now here 1 and 1 will cancel. So it is equal to 2 times mod of sin theta by 2. Now we know that theta is greater than or equal to sin theta. So basically we can write mod of sin theta by 2 will be less than or equal to mod of theta by 2. So now we can write this is less than or equal to 2 times mod theta by 2. 2 and 2 will cancel and mod of theta is argument of z, which is what we need to prove in this question.
So let us take another question in limits, which is limit theta tends to 0, greatest theta function of n sin theta upon theta plus n tan theta upon theta, where n is a positive integer and this box represents greatest integer function. Now what I know is theta is a very small number. So from calculus inequality I can say sin theta is less than theta is less than tan theta. So if I'll multiply it by theta, I can write it as sin theta upon theta is less than 1 and it is less than tan theta upon theta. Now I'll need n sin theta and n tan theta. So I'll multiply it by n. So this is n sin theta upon theta is less than n and it is less than n tan theta upon theta. I cannot take this limit inside this greatest integer function, because in that case it will be sin theta upon theta is 1. So it is n, which is an integer. So at integral points, greatest integer function is discontinuous. So I cannot take this limit inside either of these two expressions. Now, looking at this first expression, I know sin theta upon theta is 1. So this value n sin theta upon theta is nearly n, but exactly not equal to n, little less than n. So in that case, greatest integer function of n sin theta upon theta, it will be n minus 1. In the same way, this n tan theta upon theta, so tan theta upon theta is nearly 1, but still little greater than 1. So n tan theta upon theta is little greater than n. So that is greatest integer function of n tan theta upon theta is equal to simply n. So if I'll put this value in this limit, I'll get this result as, so this is n minus 1 plus n. So this is 2n minus 1. So answer to this limit is simply 2n minus 1.
Now the seventh inequality we have is rearrangement inequality. In rearrangement inequality, we have two sequences of real numbers arranged in some order, either ascending or descending. Suppose we have two sequences, A1 is less than equal to A2 is less than equal to A3 and is less than or equal to AN. In the same way, we have another sequence, B1, B2 is less than equal to B3 is less than equal to Bn. So we have two sequences, AI and Bi, and they are arranged in some fashion. In this case, they are both arranged in ascending order. Now we'll define some of their products. So if we multiply them in the same order, we'll say it is capital M. Here we are multiplying A1 with B1. So it will be this A1 B1 plus A2 B2, and it goes all the way up to AN Bn, and we call it capital M. And if we are multiplying them in the opposite order, that means suppose we are taking A in ascending order and we are taking B in descending order, and we are multiplying the corresponding terms, then we'll say it is small m, and it will be given by A1 Bn, A2 Bn minus 1, A3 Bn minus 2 up to An B1. That's your small m. So capital M is when we are multiplying them in the same order, and small m is when we are multiplying them in the opposite order. And suppose we have any other permutation of B, which is suppose pi B. Here we have arranged them in any random order. Suppose the sequence is B3, B1, B5, B7, any random arrangement of B. And we define this sum of products as capital X, and it is A1, B pi 1, A2, B pi 2 up to An, B pi m. Then rearrangement inequality says this m is always less than equal to x, and it is always less than or equal to capital M. And that's a rearrangement inequality. So sum of products of corresponding terms will be maximum if we are multiplying and adding them in the same order, and it will be minimum if we are multiplying and adding them in opposite order, and for any random multiplication it will always lie between minimum and maximum value. So this is how we are going to use rearrangement inequality. Now let us take up an example. So we'll prove Nesbit's inequality using rearrangement inequality. अब चलते हैं हमारे चौथे मेथड की तरफ, जिसको हम बोलते हैं रीअरेंजमेंट इनइक्वालिटी. तो एक क्वेश्चन में विदाउट लॉस ऑफ जनरलिटी अपने अज्यूम कर सकते हैं A is greater than equal to B and it is greater than or equal to C. अब A B से बड़ा है और B C से बड़ा है. अगर यहां पे हम देखें तो सबसे बड़ा क्या होगा? a प्लस बी, ये बड़ा होगा आपका a प्लस सी से, और ये बड़ा होगा आपका b प्लस सी से। तो अगर इसका रेसिप्रोकल ले लिया तो ये सीक्वेंस इन्वर्ट हो जाएगा, तो इसको लिख सकते हैं 1 अपॉन a प्लस बी इज लेस देन इक्वल टू 1 अपॉन c प्लस a, दैट इज लेस देन इक्वल टू 1 अपॉन b प्लस c। तो यहां पे हमारे पास दो सीक्वेंसेस आ गए, पहला a ग्रेटर देन इक्वल टू b इज ग्रेटर देन इक्वल टू c, और दूसरा 1 अपॉन b प्लस c इज ग्रेटर देन इक्वल टू 1 अपॉन c प्लस a एंड b ग्रेटर देन इक्वल टू 1 अपॉन a प्लस b। अब हमको पता है अगर इनको सेम ऑर्डर मल्टीप्लाई करेंगे तब इनका सम मैक्सिमम आएगा। तो इसका जो मैक्सिमम सम होगा वो होगा a अपॉन b प्लस c प्लस b अपॉन c प्लस a प्लस c अपॉन a प्लस b। तो ये हो गया इसका मैक्सिमम वैल्यू। अब अपने इसका एक परम्यूटेशन कंसीडर करते हैं। सपोज हम परम्यूट कर रहे हैं सेकेंड सीरीज को, और अब हम इसको परम्यूट कर रहे हैं 1 अपॉन c प्लस a, 1 अपॉन a प्लस b और 1 अपॉन b प्लस c के फॉर्म में। तो इसका जो प्रोडक्ट आएगा वो आएगा a अपॉन c प्लस a प्लस b अपॉन a प्लस b प्लस c अपॉन b प्लस c, जो कि हमेशा छोटा होगा या बराबर होगा इसके मैक्सिमम वैल्यू के, जो कि है a अपॉन b प्लस c प्लस b अपॉन c प्लस a प्लस c अपॉन a प्लस b के। तो ये है हमारा पहला रिजल्ट। अब हम क्या करेंगे, अब हम इसका एक और परम्यूटेशन कंसीडर करेंगे, और यहां पे हम इसको लिखेंगे 1 अपॉन a प्लस b, 1 अपॉन b प्लस c और 1 अपॉन c प्लस a के। तो यहां से ये हो जाएगा आपका a अपॉन a प्लस b प्लस b अपॉन b प्लस c प्लस c अपॉन c प्लस a, एंड दिस इज लेस देन इक्वल टू a अपॉन b प्लस c प्लस b अपॉन c प्लस a प्लस c अपॉन a प्लस b, और ये है हमारा सेकेंड रिजल्ट। अब क्या करते हैं, दोनों को ऐड कर देते हैं। तो दोनों को ऐड कर देंगे तो अगर हम यहां देखें a अपॉन c प्लस a प्लस c अपॉन c प्लस a, तो ये हो गया आपका 1। इसी तरीके से b अपॉन a प्लस b प्लस a अपॉन a प्लस b, ये भी हो गया 1, और c अपॉन b प्लस c प्लस b अपॉन b प्लस c, ये भी हो गया 1, एंड दिस इज लेस देन इक्वल टू 2 टाइम्स a अपॉन b प्लस c प्लस b अपॉन c प्लस a प्लस c अपॉन a प्लस b के। तो यहां से इसको रीअरेंज करेंगे तो इसको हम लिख सकते हैं a अपॉन b प्लस c प्लस b अपॉन c प्लस a प्लस c अपॉन a प्लस b, इट इज ग्रेटर देन और इक्वल टू 3/2, जो कि हमको प्रूव करना था। लेट अस टेक अप एन एग्जांपल। से फॉर एग्जांपल द क्वेश्चन इज इफ x lies between 0 and pi/2, then minimum value of cos cube x upon sin x plus sin cube x upon cos x is. Now one of the sequences, suppose cos cube x and sin cube x, and they are arranged in some order, then cos x and sin x, so they'll be arranged in the same order, but 1 upon cos x and 1 upon sin x will be arranged in the opposite order. Now we know that if we multiply them in the opposite order, then sum of product is minimum. So in this case, this small m, it will be this cos cube x upon cos x plus sin cube x upon sin x. And if we take any random arrangement where we have taken cos cube with sin, then this x will be cos cube x upon sin x plus sin cube x upon cos x. Now this is 1, and we know that this x, it is always greater than or equal to small m. So from here we can say this cos cube x upon sin x plus sin cube x upon cos x is always greater than or equal to 1. So its minimum value is 1, and that's your option D. Now the eighth inequality we have is Chebyshev's inequality. Now this Chebyshev's inequality, it is a general form of rearrangement inequality. Now in this also, we'll have two sequences which are arranged in an ordered way. Say A1 is greater than equal to A2 is greater than equal to A3. It goes on up to greater than equal to AN, and then we have another sequence B1 is suppose greater than equal to B2 is greater than equal to B3 is greater than equal to Bn. Then this Chebyshev's inequality says if we multiply them in the same order, then A1 B1 plus A2 B2 plus AN Bn upon n, it will be greater than or equal to A1 plus A2 up to AN by n into B1 plus B2 plus Bn by n. And if we take them in opposite order, so this is same order, but if we take them in opposite order, then A1 Bn plus A2 Bn minus 1 up to AN B1 upon n, it will be less than or equal to A1 plus A2 plus AN by n into B1 plus B2 plus Bn by n. So this is your Chebyshev's inequality. Now let us take up an example. Now here the question is, let A, B, C be positive real numbers, then show that AB upon A plus B plus BC upon B plus C plus CA upon C plus A is less than or equal to 3 times AB plus BC plus CA upon 2 times A plus B plus C. Now we can also write this as 1 upon A plus 1 upon B plus 1 upon B plus 1 upon C plus 1 upon C plus 1 upon A. It is less than or equal to 3 times AB plus BC plus CA upon 2 times A plus B plus C. Now, without loss of generality, we can assume that A is greater than or equal to B and it is greater than or equal to C, or we can say 1 upon A will be less than 1 upon B and will be less than 1 upon C. Now further we can say this 1 upon A plus 1 upon B will be less than or equal to 1 upon A plus 1 upon C and will be less than or equal to 1 upon B plus 1 upon C. And if we take its reciprocal, then we can write 1 upon A plus 1 upon B will be greater than or equal to 1 upon C plus 1 upon A and will be greater than or equal to 1 upon B plus 1 upon C. So from here we can say AB upon A plus B will be greater than or equal to CA upon A plus C will be greater than or equal to BC upon B plus C. So this is our first result, and we also know A plus B will be greater than or equal to A plus C and will be greater than or equal to B plus C, and that's our second result. Now we have two sequences which are arranged in the same order. So here we are going to use Chebyshev's inequality. Now Chebyshev's inequality says if we multiply them in the same order, then it will be this AB plus CA plus BC upon 3 will be greater than or equal to AB upon A plus B plus CA upon A plus C plus BC upon B plus C by 3 into A plus B plus B plus C plus C plus A upon 3. Now here this 3 and 3 will cancel. So we can write AB plus BC plus CA will be greater than or equal to 1 by 3. And this is AB upon A plus B plus CA upon C plus A plus BC upon B plus C into 2 times A plus B plus C. And if we rearrange, we can write AB upon A plus B plus BC upon B plus C plus CA upon C plus A. It is less than or equal to 3 times AB plus BC plus CA upon 2 times A plus B plus C, which is what we need to prove in this question. Now let us take another example, and it says if ABC XYZ be positive real numbers such that A plus B plus C is 7 and X plus Y plus Z is equal to 15, then what is the smallest possible value of AX plus BY plus CZ? Now without loss of generality, if we assume them in the same order, then we know that AX plus BY plus CZ upon 3 will be greater than or equal to A plus B plus C by 3 into X plus Y plus Z upon 3. Now this 3 and 3 will cancel, so we can write AX plus BY plus CZ will be greater than or equal to A plus B plus C, which is 7, X plus Y plus Z, it is 15 by 3, this is 5, it is 35. So the smallest possible value of AX plus BY plus CZ will be 35, and that is the answer to this question. Now here the question is, we need to prove that x square upon y plus z plus y square upon z plus x plus z square upon x plus y is greater than or equal to x plus y plus z upon 2. Now again for this, we'll assume x is greater than or equal to y, it is greater than or equal to z, then x square will be greater than or equal to y square and will be greater than or equal to z square. Now if we look at the sum, then y plus z will be less than or equal to x plus z and will be less than or equal to x plus y, or 1 upon y plus z will be greater than or equal to 1 upon z plus x and will be greater than or equal to 1 upon x plus y. Now these two sequences, they are in the same order. Then using Chebyshev's inequality, we can write x square upon y plus z plus y square upon z plus x plus z square upon x plus y whole divided by 3 will be greater than or equal to x square plus y square plus z square upon 3 into 1 by 3, and here we'll have 1 upon y plus z plus 1 upon z plus x plus 1 upon x plus y. Now this 3 and 3 will cancel. From here we can write x square upon y plus z plus y square upon z plus x plus z square upon x plus y will be greater than or equal to x square plus y square plus z square, and this is 1 by 3, and here we have 1 upon y plus z plus 1 upon z plus x plus 1 upon x plus y. Now here what we are going to do is we are going to use nth power am formula. So we'll consider 3 numbers y plus z, we'll write y plus z to the power minus 1 plus z plus x to the power minus 1 plus x plus y to the power minus 1 upon 3. It will be greater than or equal to y plus z plus z plus x plus y upon 3 to the power minus 1. So from here we can say this 1 upon 3, 1 upon y plus z plus 1 upon z plus x plus 1 upon x plus y, it will be greater than or equal to 3 upon 2 x plus y plus z. And if we substitute this result here, then we can say x square upon y plus z plus y square upon z plus x plus z square upon x plus y will be greater than or equal to x square plus y square plus z square. And if we substitute this result, it will be this 3 times upon 2 x plus y plus z. Now here we'll use power mean inequality. Now for power mean inequality, we know that m2 xyz will be greater than or equal to m1 xyz. That means x square plus y square plus z square upon 3 to the power 1 by 2, it is greater than or equal to x plus y plus z upon 3. Now if we square it, we can write x square plus y square plus z square. Now 3 and 3 will cancel, so it will be this 3 upon x plus y plus z will be greater than or equal to x plus y plus z. And if we substitute this result here, then we can write this is greater than or equal to x plus y plus z upon 2. And therefore we can write x square upon y plus z plus y square upon z plus x plus z square upon x plus y is greater than or equal to x plus y plus z whole divided by 2, which is what we need to prove in this question. Now the 9th inequality we have is reverse rearrangement inequality. In rearrangement inequality, we had sum of products, and in reverse rearrangement, we'll have product of sums. So if we have two sequences, A1 is suppose greater than or equal to A2, is greater than or equal to A3, is greater than or equal to AN, and B1 is greater than or equal to B2, is greater than or equal to B3, and is greater than or equal to Bn. So they are arranged in the same order. Now if we add the corresponding terms and multiply them, then we'll say this product of sum is small m and will be this A1 plus B1 into A2 plus B2 up to AN plus BN. So if we multiply them in the same order, then the product of this sum will be minimum. And if we multiply them in the opposite order, then we have capital M and will be this A1 plus Bn, A2 plus Bn minus 1 up to An plus B1. And in this case, product of this sum is maximum. And if we have any random permutation of B pi, which is B pi 1, B pi 2, B pi n, let us denote that product of sum as capital X. So it will be this A1 plus B pi 1, A2 plus B pi 2 up to An plus B pi n. Now this reverse rearrangement inequality says this x will always lie between capital M and small m. So if we add them in the same order, it will be minimum, and if we add them in opposite order, there will be maximum, and for any other arrangement, its value will lie between small m and capital M. Now let us take up an example. Say for example, we are given that we have n numbers x1, x2, x3 up to xn, and they are greater than or equal to 1. Then we need to prove that x1 square minus x1 plus x2 plus x2 square minus x2 plus x3 is always greater than or equal to x1 square, x2 square up to xn square. Now without loss of generality, let us assume that x1 is greater than or equal to x2, it is greater than or equal to x3, that is greater than or equal to xn for all xi greater than 1. Now if we consider this function fx, which is x square minus x, then f dash x is 2x minus 1. Here the critical point is 1 by 2, it is positive. So whenever x is greater than 1, this fx, it is an increasing function. So if fx is an increasing function, then we can write fx1 will be greater than fx2 will be greater than or equal to fx3 and will be greater than or equal to fxn. Now here we can write x1 square minus x1 will be greater than or equal to x2 square minus x2 will be greater than or equal to x3 square minus x3 and will be greater than or equal to xn square minus xn. Now if we take product of sum in same order, so both of them they are in same order, we know that this product will be minimum. So this m will be x1 square minus x1 plus x1 into x2 square minus x2 plus x2 and xn square minus xn plus xn. Now here these terms they'll cancel, so its minimum value will be x1 square into x2 square into xn square, and this product will be less than or equal to any random arrangement. Now we'll consider a random arrangement where we have this sequence and we consider another sequence which is x2, x3, x4, xn and x1. So if we take product of this sum, then it will be less than or equal to x1 square minus x1 plus x2, x2 square minus x2 plus x3 up to xn square minus xn plus x1, which is what we need to prove in this question. Now here the question is given that x, y and z are non-negative real numbers such that xy plus yz plus zx it is equal to 1, then prove that x square plus y square plus 2 into y square plus z square plus 2 into z square plus x square plus 2 is greater than or equal to 8x plus y plus z minus xyz whole square. Now if we consider this left hand side, then we can write this as this symmetric product of x square plus y square plus 2. Now we can write this as x square plus y square plus 2 into 1, and 1 is xy plus yz plus zx. So we can write this as xy plus yz plus zx. So it will be this product, and then if we take these three together, it will be x plus y whole square plus, and here if we take 2z common, we'll have x plus y, and if we take x plus y common, then it will be this product x plus y into x plus y plus 2z. So in this we have changed our left hand side to this expression. In the same way we can change our right hand side also. Now this right hand side is 8 x plus y plus z minus xyz whole square. Now we can also write this as 8 and this is xyz minus x plus y plus z whole square, and we'll consider this 1 here, then we can write xy plus yz plus zx whole square. Now this is 8 xyz and then minus x square y plus xyz plus zx square xy square plus y square z plus xyz plus zxy plus yz square plus z square x whole square. Now we can also write this as x square y plus xy square plus yz square plus zy square plus xz square plus zx square plus 2 xyz whole square. Now if we simplify the cyclic expression, we can write this as 8 and this is x plus y, y plus z and z plus x whole square. So basically, rather than proving the given expression, we'll prove that this product x plus y into x plus y plus 2z, it is greater than or equal to 8 times x plus y, y plus z, z plus x whole square. Now we know that this pi x plus y is x plus y into y plus z into z plus x, which will cancel one time. So we can write pi x plus y plus 2z, it is greater than or equal to 8 times x plus y, y plus z to z plus x, which is what we need to prove. Now what we'll do is we'll let x plus y as a, z plus x as b, and y plus z as c. Then we can write this as this product, and then x plus z, it is b, and y plus z is c. So product b plus c, it is greater than or equal to 8 abc. Now if we use reverse rearrangement for abc, then we can write pi b plus c will always be greater than or equal to pi b plus b, which is in the same order, which is pi 2b, and pi 2b is simply 2b into 2c into 2a. So from here we can write this pi b plus c, it is greater than or equal to 8 abc, which is what we need to prove in this question. Now the 10th inequality that we'll study is Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. So if we have two n real numbers, a1, a2, an, and b1, b2, bn, where each of ai and bi belongs to real numbers, then Cauchy-Schwarz inequality says a1, b1 plus a2, b2 up to an, bn whole square will be less than or equal to a1 square plus a2 square up to an square into b1 square plus b2 square up to bn square. This is also called as dot product inequality, and we know that in dot product a dot b is less than or equal to mod a into mod b. So for two n real numbers, we can write a1 b1 plus a2 b2 up to an bn whole square will be less than a1 square a2 square an square into b1 square, b2 square and bn square. Now this inequality is also an important inequality which is used extensively. Let us take up an example. It says we are given real numbers a, b and c such that a square plus b square plus c square is 1. Then what is the maximum value of 12a plus 4b plus 3c? Now we'll consider 6 numbers. 3 numbers are a, b and c, and other 3 numbers are 12, 4 and 3. Now if we use Cauchy-Schwarz inequality in this, we can write 12a plus 4b plus 3c whole square will be less than equal to a square plus b square plus c square into 12 square plus 4 square plus 3 square. Now this is 12a plus 4b plus 3c whole square and will be less than equal to, now a square plus b square plus c square is 1 and this is 144 plus 25 and will be this 169. So we can write 12a plus 4b plus 3c will be less than or equal to. So the maximum value of 12a plus 4b plus 3c is 13 and that is the answer to this question. Now the next question is for positive reals a, b and c. So we have 3 positive real numbers a, b and c and we have to prove that a, b, c into a plus b plus c, it is less than or equal to a cube b plus b cube c plus c cube a. Now for this what we'll do is we'll consider 6 numbers of which first 3 numbers are a upon root c, b upon root a and c upon root b, and the other 3 numbers are root c, root a and root b. Now using Cauchy-Schwarz inequality on this, we can write a upon root c into root c plus b upon root a into root a plus c upon root b into root b whole square will be less than or equal to a square upon c plus b square upon a plus c square upon b into a plus b plus c. Now this is a plus b plus c whole square, so we can cancel a plus b plus c, so we can write a plus b plus c will be less than a square upon c plus b square upon a plus c square upon b. And if we take reciprocal and cross multiply, then we can write ABC into a plus b plus c. It is less than equal to a cube b plus b cube c plus c cube a, which is what we need to prove in this question. अब हम आते हैं 5वें मेथड पे जो कि है Cauchy-Schwarz inequality. तो ये मेथड यूज करने से पहले Cauchy-Schwarz inequality पढ़ लेते हैं. अब ये मेथड कहता है अगर हमारे पास 2 सेट ऑफ नंबर्स हैं a1 a2 an b1 b2 bn, तो a1 स्क्वायर प्लस a2 स्क्वायर प्लस an स्क्वायर इंटू b1 स्क्वायर प्लस b2 स्क्वायर अप टू bn स्क्वायर हमेशा बड़ा होगा या बराबर होगा a1 b1 प्लस a2 b2 प्लस an bn होल स्क्वायर से. अगर इसको बेसिकली देखें तो ये हमको डॉट प्रोडक्ट के जैसे लगता है. हमको पता है a डॉट बी मॉड बी कॉस थीटा है और कॉस थीटा का मैक्सिमम वैल्यू 1 है. तो ये बेसिकली इनर डॉट प्रोडक्ट है टोपोलॉजी में, जिसके रिजल्ट को हम यहाँ इनइक्वालिटी के जैसे यूज करते हैं. तो वापस आते हैं इस क्वेश्चन की तरफ. तो अब इस क्वेश्चन के लिए हम क्या करेंगे, हम 2 सेट ऑफ वेक्टर्स लेंगे. पहला वेक्टर है हमारा अंडर रूट ऑफ a प्लस बी, अंडर रूट ऑफ b प्लस सी, अंडर रूट ऑफ सी प्लस ए, और दूसरा सेट ऑफ वेक्टर है हमारा 1 अपॉन अंडर रूट ऑफ ए प्लस बी, 1 अपॉन अंडर रूट ऑफ बी प्लस सी, और 1 अपॉन अंडर रूट ऑफ सी प्लस ए। अब a1 स्क्वायर, a2 स्क्वायर और a3 स्क्वायर, तो ये हो जाएगा आपका a प्लस बी प्लस बी प्लस सी प्लस ए, और यहां पे हो जाएगा आपका 1 अपॉन ए प्लस बी प्लस 1 अपॉन बी प्लस सी प्लस 1 अपॉन सी प्लस ए, एंड दिस इज ग्रेटर देन और इक्वल टू a1 b1, तो ये हो गया 1 प्लस 1 होल स्क्वायर के, तो ये हो गया आपका 2 टाइम्स a प्लस बी प्लस सी, तो इसको हम लिख सकते हैं 2 टाइम्स a प्लस बी प्लस सी, और ये हो गया 1 अपॉन ए प्लस बी प्लस 1 अपॉन बी प्लस सी प्लस 1 अपॉन सी प्लस ए, एंड दिस ग्रेटर देन और इक्वल टू 9। अब इस 2 को इधर ले जाते हैं और ए बी सी को अंदर मल्टीप्लाई कर देते हैं, तो ये हो जाएगा आपका a प्लस बी प्लस सी अपॉन ए प्लस बी प्लस सी अपॉन बी प्लस सी, और a प्लस बी प्लस सी अपॉन सी प्लस ए, एंड दिस इज ग्रेटर देन इक्वल टू 9/2। अब ये एक्सप्रेशन को हमने ऑलरेडी सॉल्व किया था जब हमने सबसे पहला मेथड देखा था AMHN, तो यहाँ पे हम 2 पार्ट में स्प्लिट करेंगे, a प्लस बी अपॉन ए प्लस बी प्लस सी अपॉन ए प्लस बी कट जाएगा, तो ये हो गया 1 प्लस सी अपॉन ए प्लस बी। इसी तरीके से ये हो गया आपका 1 प्लस ए अपॉन बी प्लस सी, और ये हो जाएगा आपका 1 प्लस बी अपॉन सी प्लस ए, एंड दिस इज ग्रेटर देन इक्वल टू 9/2। अब इसको रीअरेंज करेंगे, तो ये हो जाएगा आपका a अपॉन बी प्लस सी प्लस बी अपॉन सी प्लस ए प्लस सी अपॉन ए प्लस बी, दिस इज ग्रेटर देन इक्वल टू 9/2 माइनस 3, एंड 9/2 माइनस 3 इज 3/2। तो ये है आपका प्रूफ Cauchy-Schwarz inequality के साथ। Now one of the direct consequence of Cauchy-Schwarz inequality is Titu's lemma. Now, Titu's lemma says, if we have a sequence of real numbers, say a1, a2 up to an, and a sequence of positive real numbers b1, b2 and bn, so this first sequence, it is a sequence of real numbers, and this second sequence, it is a sequence of positive reals, then this Titu's lemma says a1 square upon b1 plus a2 square upon b2 up to an square upon bn, it is always greater than or equal to a1 plus a2 up to an whole square upon b1 plus b2 up to bn. Now let us take an example. Here we have to prove that x square upon y plus z plus y square upon z plus x plus z square upon x plus y is greater than or equal to x plus y plus z by 2, where x, y and z are positive real numbers. Now what we'll do is we'll consider a sequence of numbers x square, y square, z square, and a sequence of positive numbers y plus z, z plus x and x plus y. Now using Titu's lemma, we can write x square upon y plus z plus y square upon z plus x plus z square upon x plus y. It is greater than equal to, now this is a1 plus a2 up to an whole square, so it will be this x plus y plus z whole square upon, and this is b1 plus b2 up to bn, so it will be y plus z plus z plus x y, which is 2 times x plus y plus z. Now this x plus y plus z will cancel once, and it is equal to x plus y plus z upon 2, which is what we need to prove in this question. जो हमारा छठा मेथड है सॉल्व करने का, वो भी Cauchy-Schwarz से रिलेटेड है। Cauchy-Schwarz inequality से एक लेमा आता है जिसको हम बोलते हैं Titu's lemma। तो ये लेमा ये कहता है, अगर हमारे पास एक सीक्वेंस है n रियल नंबर्स का, जो कि है सपोज x1 x2 अप टू xn, और एक दूसरा सीक्वेंस है n पॉजिटिव नंबर्स का, जो कि है सपोज a1 a2 अप टू an। तो T2's लेमा कहता है कि ये जो समेशन है xi स्क्वायर अपॉन ai, ये हमेशा बड़ा होगा या बराबर होगा समेशन xi स्क्वायर के अपॉन समेशन ai के। तो बेसिकली x1 स्क्वायर अपॉन a1 प्लस x2 स्क्वायर अपॉन a2 अप टू xn स्क्वायर अपॉन an बड़ा होगा या बराबर होगा x1 प्लस x2 प्लस xn होल स्क्वायर अपॉन a1 प्लस a2 प्लस an से। तो यहां पे x का सीक्वेंस एक रियल नंबर्स का सीक्वेंस है, जबकि a का सीक्वेंस एक पॉजिटिव नंबर्स का सीक्वेंस है। तो इस क्वेश्चन के लिए हम दो सीक्वेंसेस लेते हैं। अब पहला सीक्वेंस है हमारा जिसमें हम 3 नंबर्स लेते हैं, 1 1 और 1। तो ये है सपोज हमारा x का सीक्वेंस, और a का सीक्वेंस हम लेते हैं b प्लस c प्लस a और a प्लस b। तो अब इसमें अगर T2's लेमा यूज करते हैं तो हो जाएगा 1 अपॉन b प्लस c प्लस 1 अपॉन c प्लस a प्लस 1 अपॉन a प्लस b, और ये बड़ा होगा या बराबर होगा अब x1 प्लस x2 प्लस x3 होल स्क्वायर, ये हो जाएगा आपका 3 स्क्वायर अपॉन a1 प्लस a2 प्लस a3। तो इनको तीनों को ऐड करेंगे तो ये जाएगा 2 टाइम्स a प्लस b प्लस c। तो इसको अगर रीअरेंज करते हैं तो ये बन जाएगा आपका a प्लस b प्लस c इंटू 1 अपॉन b प्लस c प्लस 1 अपॉन c प्लस a प्लस 1 अपॉन a प्लस b, और ये बड़ा है या बराबर है 9/2 के। अब ये तो वही फॉर्म बन गया जिसको हम बार बार सॉल्व करते आ रहे हैं। तो इसको अगर सिंप्लीफाई करेंगे तो यहां से हमको मिल जाएगा a अपॉन b प्लस c प्लस b अपॉन c प्लस a प्लस c अपॉन a प्लस b, एंड दिस इज ग्रेटर देन और इक्वल टू 3/2, जो कि है हमारा छठा प्रूफ। नाउ द 11th inequality we have is Schur's inequality. Now Schur's inequality says if we have 3 non-negative real numbers x, y, z, so these are non-negative real numbers, and we have a positive real number, say t, then xt into x minus y into x minus z plus y to the power t into y minus x into y minus z plus z to the power t into z minus x into z minus y. It is always greater than or equal to 0. Now this inequality is known as Schur's inequality. Now for this inequality, if we take t as 1, then we can write this summation x, x minus y, x minus z, and this is symmetric sum. It is greater than or equal to 0, or we can write this as x cube minus x square y plus x square z plus x y z greater than or equal to 0. So from here we can write this x cube plus y cube plus z cube plus 3xyz is greater than or equal to x square y plus x square z, y square x plus y square z plus z square x plus z square y. Now we can rearrange this right hand side as x cube plus y cube plus z cube plus 3xyz, and if we take these two together we can write xy into x plus y, taking these two yz into y plus z plus xz into x plus z. And if we take t as 2, then it will be this symmetric sum of x square, and this is x minus y, x plus z greater than or equal to 0, or x square, and this is x square minus y plus zx plus yz greater than or equal to 0. And if we simplify this, we can write x to the power 4 plus y to the power 4 plus z to the power 4 plus xyz into x plus y plus z will be greater than or equal to x cube y plus x cube z, y cube z plus y cube x plus z cube y plus z cube x. So these are two standard results from Schur's inequality which we are going to use while solving inequalities. Now let us take up an example. Say for example, it says if a, b, c are non-negative real numbers such that a plus b plus c is 1, then prove that a cube plus b cube plus c cube plus 6abc, it is greater than or equal to 1 by 4. Now what we can do is we can write this as 4, and this is a cube plus b cube plus c cube plus 6abc, it is greater than or equal to 1, and we can write this one as a plus b plus c whole cube. Now this is 4 a cube plus b cube plus c cube plus 6abc, and will be greater than or equal to a cube plus b cube plus c cube plus 3 a square b plus c plus b square c plus a plus c square a plus b. Now we can cancel a cube plus b cube plus c cube, and we can cancel 3 also. Then we get a cube plus b cube plus c cube plus 8abc will be greater than or equal to a square b plus c plus b square c plus a plus c square a plus b. Now we know that since a, b, c are non-negative real numbers, then a cube plus b cube plus c cube plus 8abc will always be greater than or equal to a cube plus b cube plus c cube plus 3abc, which is greater than or equal to a square b plus c plus b square c plus a plus c square a plus b, which is standard result from Schur's theorem. So that means this inequality is true. Now let us take another example, and here we given a plus b are three positive real numbers such that a plus b is greater than or equal to c, b plus c is greater than or equal to a, and c plus a is greater than or equal to b. Then we have to prove this result. What we'll do is we'll say let a equals x plus y, b equals y plus z, and c equals z plus x. Then if we take a plus b is x plus 2y plus z, it is greater than z plus x. So from here we can write x, y and z are non-negative real numbers. Now if we substitute the value of abc here, then we can write this is 2, and then x plus y square, and b plus c is x plus y plus 2z, this symmetric sum, and will be greater than or equal to x3, and symmetric sum of x plus y whole cube plus 9 times x plus y, y plus z into z plus x. Now we can write this as 2 times summation x plus y cube plus 4 times this summation z into x plus y square. It is greater than or equal to summation x plus y cube plus 9 times x plus y plus z into z plus x. And if we are going to simplify this, we'll get x cube plus y cube plus z cube plus 3xyz, that is greater than or equal to x square y plus z plus y square z plus x plus z square x plus y, which is nothing but result from Schur's inequality when r is equal to 1. Now the 12th inequality that we are going to study is Jensen's inequality. Now it says if fx is a convex function in some interval I, and when we say it is a convex function, we mean it is concave up, or f double dash x, it must be greater than 0 for all x belongs to that interval, then w1 fx1 plus w2 fx2 up to wn fxn upon w1 plus w2 up to wn, it will be greater than or equal to f w1x1 plus w2x2 up to wn xn whole divided by w1 plus w2 up to wn. And if we take all the weights as 1, then we get this simple case, which is fx1 plus fx2 up to fxn by n. So basically it is arithmetic mean of values at x1, x2 and xn. It is greater than or equal to value of arithmetic mean of x1, x2 and xn. So it will be greater than or equal to function value of x1 plus x2 plus xn whole divided by n. And if fx is concave, then in that case sign reverses. So there we'll have this less than or equal to sign. So if we write it for this function fx, which is concave in this interval I, taking the weights as 1, we can write fx1 plus fx2 up to fxn whole divided by n. It will be less than or equal to f x1 plus x2 plus xn whole divided by n. So this inequality is known as Jensen's inequality. Here the question is, prove that in any triangle ABC we have sin A plus sin B plus sin C always less than or equal to 3 root 3 by 2. Now we know that in a triangle sum of angles is pi. So A plus B plus C is pi. Now we know that this sine function, it is a concave function in the interval 0 to pi. A, B and C, they belong to 0 to pi. Now using Jensen's inequality, we can write sin A plus sin B plus sin C upon 3 will be less than or equal to sin A plus B plus C by 3. Now A plus B plus C is pi. So we can write sin A plus sin B plus sin C will be less than equal to 3 times, and this is sin pi by 3, and sin pi by 3 is root 3 by 2. So it will be this 3 under root 3 by 2. So from here we have proved that sin A plus sin B plus sin C is less than equal to 3 root 3 by 2. Now let us take up an example. Here the question is, if fx is a continuous function and it is convex on the interval 2 to 11. So we are given fx is continuous and convex on the interval 2 to 11, and we are given that f2 equals 6, f5 equals 3, and f11 equals 15. Then using Jensen's inequality, we have to find an upper bound for the possible value of f6. Now if we use Jensen's inequality for this function, which is a convex function, we know that f2 plus f5 plus f11 by 3 will be greater than or equal to f2 plus 5 plus 11 whole divided by 3. Now f2 is 6, f5 is 3, and f11 is 15 whole divided by 3, and it is greater than or equal to f, and this is 18 by 3, and 18 by 3 is f6. So from here we can write this f6 is always less than or equal to 8. So upper bound of possible value of f6 is 8, and that is the answer to this question. Now let us take another example, and here we have to prove that under root of 1 square plus 1 plus under root of 2 square plus 1 plus under root of 3 square plus 1 up to under root of n square plus 1, it is greater than or equal to n by 2 into under root of n square plus 2n plus 5. Now for this, what we'll do is we'll consider a function fx which is under root of x square plus 1 when x is greater than 0. Now if we find its f dash x, it will be 1 upon 2 under root x square plus 1 into 2x. So it will be this x under root x square plus 1, and we find f double dash x, it will be x square plus 1, and here will be this under root of x square plus 1 minus x into 1 upon 2 under root x square plus 1 into 2x. Now here this f double dash x, it is greater than 0. That means it is a convex function. Now we are going to use Jensen's inequality for this function. We can write f1 plus f2 up to fn by n will be greater than or equal to f1 plus 2 up to n whole divided by n. Now f1 is under root of 1 square plus 1 plus under root of 2 square plus 1 up to under root of n square plus 1 divided by n, and will be greater than or equal to f, and this is n plus 1 by 2. Now we'll cancel this n with n, and we'll take this n on the right hand side. We can write under root of 1 square plus 1 plus under root of 2 square plus 1 up to under root of n square plus 1 will be greater than or equal to n, and this f n plus 1 by 2 will be under root of n plus 1 by 2 whole square plus 1. So it will be greater than or equal to n by 2, and here we'll have n square plus 2n plus 1 plus 4. So we can write under root of 1 square plus 1 plus under root of 2 square plus 1 up to under root of n square plus 1 will be greater than or equal to n by 2 into under root of n square plus 2n plus 5, which is what we need to prove in this question. अब हम आते हैं हमारे 8वें तरीके पे, और 8वां तरीका है हमारा यूजिंग जेनसेन्स इनइक्वालिटी। अब जेनसेन्स इनइक्वालिटी एक बहुत इंपॉर्टेंट इनइक्वालिटी है प्रॉब्लम सॉल्व करने के लिए। a अपॉन b प्लस सी प्लस b अपॉन सी प्लस ए प्लस c अपॉन a प्लस b, और हमको प्रूव करना है ये बड़ा है बराबर है 3/2 के। तो यहां पे हम क्या करते हैं, यहां पे हम सपोज मान लेते हैं कि लेट a प्लस b प्लस सी उसका वैल्यू है सपोज s। तो ये इनइक्वालिटी के लेफ्ट हैंड साइड को हम लिख सकते हैं a अपॉन s माइनस ए प्लस b अपॉन s माइनस बी प्लस c अपॉन s माइनस सी। अगर हम ये फंक्शन कंसिडर करते हैं f(x) जो कि है x अपॉन s माइनस x, तो हम प्रूव करेंगे कि ये जो फंक्शन है ये फंक्शन कॉन्वेक्स है 0 से लेके s के बीच में। अब क्योंकि s का वैल्यू a प्लस बी प्लस सी है और a b c तीनों पॉजिटिव हैं, तो हमारे सारे नंबर्स a b और c वो तीनों इस इंटरवल के अंदर आएंगे। तो अगर हम f डैश x निकालते हैं, f डैश x हो जाएगा आपका s माइनस एक्स होल स्क्वायर, और ये हो जाएगा आपका s माइनस एक्स, और ये माइनस x एज इट इज, और ये कितना माइनस हो तो यहाँ x कट जाएगा, और इसका सेकेंड डेरिवेटिव निकालेंगे f डबल डैश x, तो ये हो जाएगा आपका माइनस 2s अपॉन s माइनस एक्स होल क्यूब प्लस 1। तो ये फंक्शन कॉन्केव अप है, तो इसलिए ये फंक्शन कॉन्वेक्स रहेगा। तो अब जबकि हमें पता है ये फंक्शन हमारा कॉन्वेक्स है, तो यहां पे हम जेनसेन्स इनइक्वालिटी यूज कर सकते हैं। तो अब जेनसेन्स इनइक्वालिटी कहता है कि एफ ए प्लस एफ बी प्लस एफ सी बाई 3 ये बड़ा होगा या बराबर होगा एफ ए प्लस बी प्लस सी बाई 3 के। अब a प्लस बी प्लस सी वो s है, यानी इसको हम लिख सकते हैं f s बाई 3 के। अब f a है a अपॉन s माइनस ए, तो ये हो गया a अपॉन s माइनस ए, f b है b अपॉन s माइनस बी, और f c है c अपॉन s माइनस c अपॉन 3, एंड दिस इज ग्रेटर देन इक्वल टू f s बाई 3। s बाई 3 हो जाएगा s बाई 3 अपॉन s माइनस s बाई 3, जो कि है आपका 1/2। तो इस 3 को इधर ले जाते हैं, ये हो गया आपका a अपॉन s माइनस ए प्लस b अपॉन s माइनस बी प्लस c अपॉन s माइनस सी, एंड दिस इज ग्रेटर देन इक्वल टू 3/2। s माइनस ए क्या है b प्लस सी, तो ये हो गया a अपॉन b प्लस सी प्लस b अपॉन c प्लस ए प्लस c अपॉन a प्लस b बड़ा है बराबर है 3/2 से। तो ये है हमारा प्रूफ यूजिंग जेनसेन्स इनइक्वालिटी। नाउ दिस 13th inequality that we want to study is Holder's inequality. Now Holder's inequality says if we have sequences ai bi up to zi, each containing n elements, then this inequality a1 plus a2 plus an to the power lambda a into b1 plus b2 plus bn to the power lambda b up to z1 plus z2 up to zn to the power lambda z will always be greater than or equal to a1 to the power lambda a, b1 to the power lambda b up to z1 to the power lambda z plus, in the same way, we'll write it for a2, b2, z2. So a2 to the power lambda a, b2 to the power lambda b up to z2 to the power lambda z will continue up to an to the power lambda a, bn to the power lambda b up to zn to the power lambda z. This inequality holds if lambda a plus lambda b plus lambda z it is equal to 1. So sum of all these powers it must be equal to 1. Only then this Holder's inequality it is going to hold. Now one thing that we should keep in mind for Holder's inequality, we cannot get maximum or minimum value of expression from Holder's inequality, because this inequality it gives us an upper bound or a lower bound. So if from Holder's inequality we get a result that x is greater than or equal to some a, then this a may not be the least value of x. Now how do we use this inequality? For this we'll take up an example. Suppose it says we have two real numbers a and b such that a to the power 6 plus b to the power 6 equals 64. Then we have to establish an upper bound for 3a square b plus 4a b square using Holder's inequality. So in this problem we have to establish an upper bound for this expression when we are given that a to the power 6 plus b to the power 6 is equal to 64. Now for this question we'll consider three sequences. First one is 3 square 4 square. Second sequence is a to the power 6 comma b to the power 6, and this third sequence is b to the power 6 into a to the power 6. Now we have to choose their power such that sum of lambda a plus lambda b up to lambda z it is equal to 1. So we'll choose power of this as 1 by 2, this power as 1 by 3, and this power as 1 by 6. Now if we add all these three, we'll get this sum as 1. So now we can use Holder's inequality for these sequences. So we can write 3 square plus 4 square to the power 1 by 2 into a to the power 6 plus b to the power 6 to the power 1 by 3 into b to the power 6 plus a to the power 6 whole to the power 1 by 6, and it is greater than or equal to, now a1 to the power lambda, so it will be this 3, b1 to the power lambda b, so a to the power 6 to the power 1 by 3 is a square into, and this is c1 to the power lambda c, b to the power 6 to the power 1 by 6 is simply b, plus, and then this is a2, so it will be this 4, and then b square and a. Now this is under root 25, which is simply 5, and here it will be a to the power 6 plus b to the power 6 whole to the power 1 by 2 will be greater than or equal to 3a square b plus 4a b square. Now a to the power 6 plus b to the power 6, it is 64. So this value will be 8. So we can write 40 is always greater than or equal to 3a square b plus 4a b square. So the upper bound of this expression, it is 40. Now it is an upper bound, and it necessarily doesn't guarantee that the maximum value of this expression is 40. This thing you have to keep in mind whenever you are using Holder's inequality. Now let us take another example, and here it says if a, b, c are positive real numbers, then prove that a upon under root a square plus 8bc plus b upon under root b square plus 8ca plus c upon under root c square plus 8ab, it is greater than or equal to 1. Now, one way of using Holder's inequality is, if we have three sequences, suppose ABC, PQR and XYZ, then we can write A cube plus B cube plus C cube to the power 1 by 3, P cube plus Q cube plus R cube to the power 1 by 3 into X cube plus Y cube plus Z cube to the power 1 by 3 will be greater than or equal to APX plus BQY plus CRZ, or simply we can write A cube plus B cube plus C cube into P cube plus Q cube plus R cube into X cube plus Y cube plus Z cube will be greater than or equal to APX plus BQY plus CRZ whole cube. So this is an important form which is mostly used in Holder's inequality. Now here what we'll do is, we'll take this as A cube, B cube, C cube, and the same expression as P cube, Q cube and R cube. So we can write this cyclic or symmetric sum A upon under root of A square plus 8BC into this symmetric sum A upon under root of A square plus 8BC into this symmetric sum of A into A square plus 8BC, and will be greater than or equal to, now this is A cube, P cube and X cube. So if we multiply them, we'll get A cube, P cube, X cube. Now A square plus 8BC will cancel. We'll get this as A cube. So value of APX will be simply A. So it will be greater than or equal to A plus B plus C whole cube. So now we can write this symmetric sum A upon under root of A square plus 8BC whole square into, now this symmetric sum will be this A cube plus B cube plus C cube, and will be 8ABC plus 8ABC plus 8ABC, and that will be 24ABC, and will be greater than or equal to A plus B plus C whole cube. So we have written this using Holder's inequality. Now we have this one standard result, and which is A plus B plus C whole cube. It is always greater than or equal to A cube plus B cube plus C cube plus 24 ABC. Now using this result here, we can write this symmetric sum of A upon under root of A square plus 8BC whole square into A cube plus B cube plus C cube plus 24ABC will be greater than or equal to this expression. It is greater than A cube plus B cube plus C cube plus 24ABC. Now this 24ABC part will cancel. So from here we can write this symmetric sum of A upon under root of A square plus 8BC. It is greater than or equal to 1, or we can write A upon under root of A square plus 8BC plus B upon under root of B square plus 8CA plus C upon under root of C square plus 8AB. It is greater than or equal to 1, which is what we need to prove in this question. Now the 14th inequality that we're going to study is Weierstrass inequality. Now there are two forms in this inequality that we use, and this first form is if a1, a2 up to an they are positive real numbers, then for n greater than 2 we can write 1 plus a1 into 1 plus a2 up to 1 plus an will be greater than 1 plus a1 plus a2 up to an, which is very simple result. And its second form is if we have n numbers a1, a2, an such that they lie between 0 and 1, then for n greater than or equal to 2 we can write 1 minus a1 into 1 minus a2 up to 1 minus an will be greater than 1 minus a1 minus a2 up to minus an. Now let us take up an example, and it says we have to prove that 1 minus a1 into 1 minus a2 up to 1 minus an, it is less than 1 upon 1 plus Sn, where Sn is sum of all these numbers a1 plus a2 up to an, where each of ai it lies between 0 and 1. Now to prove this, what we'll do is we know that any ai will lie between 0 and 1, then ai square will also lie between 0 and 1, and 1 minus ai square will be less than or equal to 1. So from here we can write 1 minus ai will be less than or equal to 1 upon 1 plus ai. Now if we take this product over all I, then this product 1 minus ai will always be less than this product 1 plus ai. So now we can write 1 minus a1 into 1 minus a2 up to 1 minus an will be less than or equal to 1 upon 1 plus a1 plus 1 plus a2 up to 1 plus an. Now we also know that 1 plus a1 into 1 plus a2 up to 1 plus an will be greater than 1 plus a1 plus a2 up to an, which is 1 plus Sn, and if we take the reciprocal, then 1 upon 1 plus a1, 1 plus a2, 1 plus an will be less than 1 upon 1 plus Sn. So it will be less than 1 upon 1 plus Sn. So from here we can write 1 minus a1 into 1 minus a2 into 1 minus an will always be less than 1 upon 1 plus Sn, which is what we need to prove in this question. Now let us take another example, and it says if n is a positive integer, then prove that 1 into 3 into 7 up to 2 to the power n minus 1 upon 2 into 4 into 8 up to 2 to the power n will be less than 2 to the power n upon 2 to the power of n plus 1 minus 1. Now we can write this as 1 by 2 into 3 by 4 into 7 by 8 up to 2 to the power n minus 1 upon 2 to the power n, or we can write this as 1 minus 1 by 2 into 1 minus 1 by 4 into 1 minus 1 by 8 into 1 minus 1 upon 2 to the power n, and we know that 1 minus a1 into 1 minus a2 up to 1 minus an, it is always less than 1 upon 1 plus Sn, and Sn is 1 by 2 plus 1 by 2 square up to 1 upon 2 to the power n. Now this is nothing but a GP. So if we write this sum 1 plus 1 by 2 plus 1 by 2 square up to 1 upon 2 to the power n, we know that it will equal to a into 1 minus r to the power n, and here number of terms is n plus 1 upon 1 minus r. So it will be this 2 and then 2 to the power of n plus 1 minus 1 upon 2 to the power of n plus 1. Now this 2 and 2 will cancel. So this value, it will be 1 upon 2 to the power of n plus 1 minus 1 upon 2 to the power n. So from here we can say this 1 into 3 into 7 up to 2 to the power of n minus 1 upon 2 into 4 into 8 up to 2 to the power n will always be less than 2 to the power n upon 2 to the power of n plus 1 minus 1. And finally, our 15th inequality is Muirhead's inequality. Now this inequality simply says if we have two sequences AI and BI, which are sequences of real numbers such that AI BI belongs to R, and each sequence containing n terms such that this sequence AI, it majorizes this sequence BI. Now what does that mean? It simply means that A1, it must be greater than or equal to B1. A1 plus A2 must be greater than or equal to B1 plus B2, or in general this summation AI, where I varies from 1 to j, it must be greater than or equal to this summation I varies from 1 to j bj for all j lying between 1 and n, and this sum I varies from 1 to n ai must be equal to this sum I equals 1 to n bi. Here it should be this bi. That means a1 plus a2 up to an, it must be equal to b1 plus b2 up to bn. So if we have these conditions, then we'll say sequence AI majorizes the sequence BI. Then this Muirhead's inequality says for all non-negative xi's, then for all non-negative xi, we can write this symmetric sum of x1 to the power a1, x2 to the power a2 up to xn to the power an will always be greater than or equal to symmetric sum of x1 to the power b1, x2 to the power b2 up to xn to the power bn. If sequence AI majorizes sequence BI, then symmetric sum of x1 to the power a1, x2 to the power a2, xn to the power an is always greater than or equal to x1 to the power b1, x2 to the power b2 up to xn to the power bn. Now we take up an example. Suppose we have two sequences 5, 1 and 4, 2. Now clearly 5, it is greater than 4, and 5 plus 1 equals 4 plus 2. That means this sequence 5 1, it majorizes sequence 4 2. So now we can write this symmetric sum a to the power 5 b to the power 1 is always greater than equal to this symmetric sum a to the power 4 b square, where a and b are non-negative real numbers. So from here we can write a to the power 5 into b plus a into b to the power 5 will be greater than equal to a to the power 4 b square plus a square b to the power 4. Now let us take up an example.
अब हम आते हैं हमारे 11वें मेथड पे, और इसमें हम यूज करेंगे म्यूरहेड इनइक्वालिटी, MUIRHEAD, म्यूरहेड्स इनइक्वालिटी, कि हमको प्रूव करना है a अपॉन b प्लस सी प्लस b अपॉन c प्लस ए प्लस c अपॉन a प्लस b ये बड़ा है या बराबर है 3/2 के। अब ये जो लेफ्ट हैंड साइड है इसको हम लिख सकते हैं समेशन a अपॉन b प्लस सी, इसका साइक्लिक सम, इसको हम लिखेंगे समेशन a स्क्वायर अपॉन ए बी प्लस ए सी। अब हमने टीटूज लेम्मा पढ़ा है, और टीटूज लेम्मा ये कहता है कि समेशन एक्स आई स्क्वायर अपॉन ए आई ये बड़ा होगा या बराबर होगा समेशन एक्स आई होल स्क्वायर अपॉन समेशन ए आई के, जहां पे एक्स आई सेट ऑफ रियल नंबर्स है और ए आई सेट ऑफ पॉजिटिव नंबर्स है। तो यहां पे इसको हम लिख सकते हैं कि ये बड़ा है या बराबर है a प्लस बी प्लस सी होल स्क्वायर अपॉन, और यहां पे हो जाएगा 2 टाइम्स ए बी प्लस बी सी प्लस सी ए। तो इसको अगर एक्सपेंड करते हैं न्यूमरेटर को तो ये हो जाएगा आपका ए स्क्वायर प्लस बी स्क्वायर प्लस सी स्क्वायर प्लस 2 ए बी प्लस बी सी प्लस सी ए अपॉन 2 ए बी प्लस बी सी प्लस सी ए। यहां पे ये सेकेंड पार्ट को कैंसिल कर लेते हैं, तो इसको लिख सकते हैं 1 प्लस ए स्क्वायर प्लस बी स्क्वायर प्लस सी स्क्वायर अपॉन 2 ए बी प्लस बी सी प्लस सी ए के। अब अगर इसको देखें ए स्क्वायर प्लस बी स्क्वायर प्लस सी स्क्वायर और ए बी प्लस बी सी प्लस सी ए, तो ये जो लेफ्ट हैंड साइड है ये मोरहेड का सीक्वेंस है 2 0 0, और ये जो दूसरा सीरीज है ये है मोरहेड का सीक्वेंस 1 1 0। तो क्लियरली ये 2 1 0 1 1 0 को मेजराइज करता है। तो यानी इसका मतलब ए स्क्वायर प्लस बी स्क्वायर प्लस सी स्क्वायर हमेशा बड़ा होगा या बराबर होगा ए बी प्लस बी सी प्लस सी ए के। तो यहां से ये जो वैल्यू आएगा वो आपका 1/2 या 1/2 से बड़ा आएगा। तो यहां से हम लिख सकते हैं दिस इज ऑलवेज ग्रेटर देन इक्वल टू 1 प्लस 1/2। तो ये हो जाएगा आपका 3/2, जो कि है हमारा प्रूफ। तो ये क्वेश्चन को हमने सॉल्व किया है टीटूज लेम्मा से, जो कि एक कॉन्सिक्वेंस है कॉचीज इनइक्वालिटी का और मोरहेड्स इनइक्वालिटी से। अब हम आते हैं हमारे 12वें मेथड की तरफ, और इस मेथड में भी हम मोरहेड्स इनइक्वालिटी का यूज करेंगे। अब इसके लिए हम क्या करेंगे, ये जो हमें दिया है a अपॉन बी प्लस सी प्लस बी अपॉन ए प्लस सी प्लस सी अपॉन ए प्लस बी, ये बड़ा है या बराबर है 3/2 के। तो हम इसको सिंप्लीफाई करेंगे, तो ये हो जाएगा a इंटू ए प्लस सी ए प्लस बी प्लस बी इंटू बी प्लस सी ए प्लस सी प्लस सी इंटू बी प्लस सी ए प्लस सी, और ये बड़ा है या बराबर है 3/2 इंटू बी प्लस सी ए प्लस सी एन ए प्लस बी के। अब ये सिंप्लीफिकेशन हम पहले ही कर चुके हैं, तो हम वापस से इसको सिंप्लीफाई नहीं करेंगे, तो हम डायरेक्ट इसका रिजल्ट लिखेंगे। तो सिंप्लीफिकेशन के बाद ये आता है आपका 2 टाइम्स a क्यूब प्लस b क्यूब प्लस c क्यूब इज ग्रेटर देन इक्वल टू a स्क्वायर b प्लस ba स्क्वायर b स्क्वायर c प्लस c स्क्वायर b प्लस a स्क्वायर c प्लस c स्क्वायर a। तो अब ये लेफ्ट हैंड साइड को देखें तो ये मोरहेड का 300 है, और ये जो राइट हैंड साइड है ये मोरहेड का 210 है, और ये पहला सीक्वेंस दूसरे सीक्वेंस को मेजराइज करता है। तो मोरहेड्स इनइक्वालिटी से ये रिजल्ट ट्रू है, तो इसका मतलब ये कंडीशन भी आपका ट्रू होगा। तो ये है हमारा 12वां प्रूफ।